Hello and welcome to another video on waves. Specifically today we're going to talk about standing waves. We've talked a decent amount about traveling waves, waves that propagate through and we can see them move. And we've done a lot of the work with pulses. Today we're going to take a look at a specific scenario. So imagine we have a pulse, in this case a single pulse traveling through. And the pulse, in this case, there's no damping, there's no friction, will continue on forever. Once I set it going with my hand, it'll keep going. The question then comes, what happens if I make another pulse? We've seen it already happen when you have two pulses, for instance. They will start to interfere with each other destructively when they're both facing opposite directions, like so, or constructively when they're both facing the same direction, like so. Today we're going to look at instead what happens if I were to say, instead of having two pulses, I instead time my pulse such that right as it comes back, I introduce the other one. Now, if I do it in this case, they cancel out almost to zero. I'm not perfect, I'm not flawless, but the antenna is still there. But what happens if I did it so they add together? So in this case, it's going to reflect, and as it reflects, right here, I add another pulse, and it gets bigger. If I do this again, right as it gets back, right here, it gets bigger still. And if I keep this process going, I'll keep getting bigger and bigger pulses. Now the trick here is that I have to do it at the exact right time. I have to have this be done in synchronization. This is fairly easy with the pulse I can watch coming in, but the moment damping gets involved, the moment friction gets involved, it becomes a lot more difficult. In fact, most of the time when I do this, I make horrible mistakes and get odd misshapen things. But if I kept doing this long enough, I would start getting bigger and bigger pulses. And this build up, this idea of a continually added energy contained to a finite spot, is what we refer to as a standing wave. Whereas instead of using pulses, I use a continuous wave. And the energy will keep adding onto itself, pulsing back and forth, until we get a pattern similar to this that adds up. Now you'll notice here there's some slight desynchronization between the addition and the current wave, which means it's not perfect. But even so, we start to see a wave pattern form. We have a crest, a trough, a slight deviation here, but we have a point in the middle here, right here, where it seems like it doesn't move at all, or very little, depending on how good it is. Like here, it stays still for a few moments before ultimately the interference, the desynchronization, throws it off. But what if we move perfectly? What if we weren't limited by these constraints? Here we have a wave. In this case, you're moving the red end, and it's going to continue through. And it's going to hit here. And it's going to reflect back along the blue one. This is a fixed end node. And as I let it go, the two of these waves are going to start interfering. And what we'll see is the steady interference and pattern here, which will result in a wave. Now this isn't perfect. We need to be slightly off kilter to make it even better. Let's go ahead and do so. Here we see a full wave. This right here is a standing wave. Now there are some key parts to a standing wave. Key things to notice. First of all, we have these points that are fixed, unmoving. We refer to these as nodes. They are solid standalone points that don't move. Next, we have the points that are actually vibrating. We refer to the points with the most extreme vibrations or extensions as antinodes. You can find them here and here. Whenever you make a slinky vibrate or move at a certain speed, you'll get these nodes and antinodes provided you get it moving back and forth fast enough. Now, this is still said to be a wave. You'll still see that there is a frequency and a wave speed, and we can even measure the wavelength here. But how do we have a wave speed when we don't have any movement? All we'd see is this green section. Well, there's still a rate the wave will propagate. It's based on the media. In this case, the media that we're using has a wave speed of 100 centimeters per second. But we can also calculate it using various calculations. For instance, if we measure from end to end, we get a wavelength. We can still measure that and calculate values using that. And further, if we measure the amount of time it takes for this crest here to go down and back up, we can get a period. And that period can be translated to a frequency. Frequency times wavelength is still wave speed. Just because this is a standing wave as opposed to a traveling wave we've been used to, we still will get a wave speed out of these calculations. Standing waves are unique in that there is a idealized length or string you could use. In this case, having a full wave encaptured in the length of a string gives us a frequency at which this will work optimally. If we looked at the original simulation, we'll notice that when things aren't quite perfectly in sync with that natural length of the string, the standing wave doesn't propagate quite properly. We refer to these natural divisions, natural ways of splitting up a wave, as harmonics. The easiest way to think of a harmonic is based on how many parts of a wave you see. There is a flat line here, which is non-existent. But if we go to the first harmonic, we have one antinode, one moving part, which is why this is typically referred to as the first, because there's one antinode. But the way I tend to think about it is half of a wavelength fits perfectly on a string. Perfectly fits every time. If we switch to the next harmonic, the second harmonic, there are 2 antinodes and a full wavelength fits on the string. These are natural frequencies of vibration that will produce for the given wave speed and length of our string a perfect fit. You'll notice that when I went from the first harmonic of 0.67 hertz to the next harmonic, it is 0.134. When I go to the harmonic after that, the third harmonic, my frequency has gone up again, and it's the 3 times the original harmonic, and I have 3, 1, 2, 3 antinodes, and this will continue to repeat. To summarize, every vibrating object that is treated as a standing wave has both a frequency and a wavelength, and a wave speed that we can calculate. When you operate a standing wave at a particular frequency so that multiples of half of the wavelength match the length of the string, you get what called harmonics. The first harmonic is when half a wavelength is and one antinode. The second harmonic is when a full wave is there and you have 2 antinodes. The third is when you have 3 antinodes and 1.5 wavelengths, and so on. Anyways, thanks for watching. Have a good one.